In this video, I'm going to go over AP Precalculus topics 2.1 through 2.8. So this includes exponential functions as well as composition of functions and inverses. So in 2.1, we were introduced to arithmetic and geometric sequences. So arithmetic sequences are sequences that are developed by adding some common difference to get from term to term, versus a geometric, we are multiplying to get from term to term. So here, we've got some different sequences. In this first one, we are adding to get from term to term. Okay, so we're adding 3, adding 3, adding 3. So this is arithmetic. Okay, where our common difference is 3. Here we can plainly see, instead of adding 3, we are multiplying by 3. So 1 times 3 is 3, 3 times 3 is 9, 9 times 3 is 27. So this is geometric, and that common ratio is 3. Here, if I'm adding, we'd add 3, add 5, add 7, so it's not arithmetic. And then I'm multiplying by 4, but if I multiply that by 4, I'd get 16, not 9. So this one is neither. Okay, here, to get from 1 to negative 1/2, we're multiplying by negative 1/2. And if I repeat that, that's our pattern of multiplying. So this is geometric. And that common ratio is a negative 1/2, which it can be. It makes the terms alternate and then get smaller, but they are still multiplying. And then here I'm subtracting 7, subtracting 7. So this is arithmetic again, where that common difference is a negative 7. So just like with geometric, we can have a negative common difference. Okay. Next, we're going to be working with arithmetic sequences. And given some information, we're going to find an equation for the nth term, an, of the arithmetic sequence. Then we're going to find the 10th term of the sequence. Before this, let's look at some equations. We're going to have two general formulas for finding the nth term of an arithmetic sequence. The first one, an, if you know the initial term, so if you know a0, then it's just going to be that first term plus n times however many differences you want. If you don't know the first term, then we're going to use a k. So an instead of a naught is going to be a k, and then we're still going to add on d, but we're going to add on n minus k of those. Now that second one is going to work if I have a 0, because if I plugged in a 0, this would be 0, and that would be 0, and you'd end up with this equation. This is equivalent to what you would know as the point-slope form of a line, where my common difference is my slope, and then ak is some point on our line. This is just going to be some term in our sequence. Okay, so in this first one, we have a 3 is 8 and a 7 is 20. So I'm going to use an equals ak plus d n minus k. Okay. My ak, you can use either, but I tend to use the smaller of the two, or the lower in the sequence. So I'm going to make this a 7, makes this a 3, plus d 7 minus 3. So what we're using these two terms is to find our common difference. So a7 is 20, a3 is 8, okay. And then it's just some quick algebra. So 12 equals 4d, so my common difference is 3. With that, I can find the formula for the nth term. Okay, still using that a3 equals 8 term. And you could simplify this down if you wanted to, but we're just using it to find a10. So I'm just going to go ahead and plug in 10. Or you can distribute and simplify, that's fine too. So we'd get 21 plus 8 would be 29. Okay, same task, different values. So AN equals AK plus DN minus K. So I'll plug in negative 23 over here equals A2 is negative 3 plus D7 minus 2. So my D here is a negative 4. So then my equation for AN is going to be negative 3 minus 4 and minus 2. And then we'll plug in 10. So 10 minus 2 is 8. 4 times 8 is 32. So negative 3 minus 32 gives me a negative 35. When we graph an arithmetic sequence, it has the appearance of a line. It has the same behavior, except it's discrete points rather than being continuous. So I'm going to, same task, I'm going to write a formula for AN. This time, since I know my initial term, I'm going to use A naught plus DN, but the other one works too. From the graph, I can see that I'm going up 2 for every term. Then I can plug in 10. Okay, here I'm given some terms in this sequence. I'm actually not given all of them since we skip, so it goes from 2 and skips over to 4, but we still have that appearance of a line. Okay, so I'm going to use 2, 8. So AN is going to equal 8. My common difference, so even though I don't have all of the terms, I can use the pattern to fill in the missing points here, which means I'm going down 2. So that's my common difference. And then we can use that to find our A10. Get 8 times 2, negative 16. 8 and negative 16 is a negative 8. Next, we're going to deal with geometric sequences. So we have 2 formulas here. If you know the 0th term, then it's just going to be that 0th term times your common ratio to the nth power. If not, then it's going to be some other term, r to the n minus k. So here we're going to find the formula for the nth term, as well as finding g of the 6th term, g6. So my general term is this. For this particular one, we are given g2 is 9, and then my common ratio is 1/3 to the n minus 2. So whatever number here, this is my input, that's my output. So then to find g of 6 now, that's going to be 9 1/3 6 minus 2 to the 4th. So 3 to the 4th is 3 times 3 times 3 times 3, which is really the same as 9 times 9. So that's going to be 9 over 81, which reduces to 1/9. Okay, here I am not given the common ratio, so we need to find it. So we're going to plug those into our formula. I guess I should write the general formula, but I did not. Sorry. So negative 8 equals r cubed, which means my common ratio is a negative 2. So my general formula is going to be gn equals 1 times r, which is negative 2, to the n minus 2. And we'll find g of 6. So negative 2 to the 4th is a 16. Okay, next I have a geometric sequence presented on the graph. Okay, so I have my initial term, and if you look, we're going 16, negative 8, positive 4, negative 2, positive 1, and so on. So my initial value is 16. The common ratio is a negative 1/2. So then if I want to find g of 6, that's going to be negative 1/2 to the 6. So 2 to the 4th is 16, 5th is 32, 6 is 64. So this will be a negative 16 over 64. Actually positive, because it's even power. That reduces to 2 over 8, which is 1/4. So let's go, 1/4. Okay. Next we have a similar idea with arithmetic and geometric sequences, but now we're converting them to linear functions and exponential functions. Linear functions behave like arithmetic sequences in that they go up by a constant rate. Exponential, we are multiplying to get from term to term. So in these table of values, we're going to determine if we've got a linear function, an exponential function, or neither. So here, to get from negative 1/4 to 1/2, we're multiplying by 2, negative 2, multiplying by negative 2, multiplying by negative 2. So this is going to be exponential. Okay, and then my reason. Okay, so for our justification, over equal length input value intervals, the output values change proportionally. This next one here, we're negative 1, 2, negative 3, 4. So if we got rid of the negatives, we'd have a linear function, but with those negatives, this is neither. Here I can see that we're going down 4 each time, and we've done this a lot, so we know this is linear. For linear over equal length input value intervals, the output values change at a constant rate, or the rate of change is constant, or the change is constant. Now with linear, you don't actually need the over equal length if you're doing the rate of change, but if we're looking at the first differences, then we do need that equal length input value interval. My last one here, we're multiplying by 5 each time, so that one is going to be exponential. For the same over equal length input value intervals, the output values change proportionally. Okay, for exponential growth and decay, we're looking at the general equation ab to the x, where a is greater than 0. Okay. If the b value is between negative 1 and 1, then we have exponential decay. If the b value is greater than 1, then we have exponential growth. So this first one is decay, because my b is between 0 and 1. Here my function is growth, exponential growth, because that b is greater than 1. And I've got one more, 1.01 is bigger than 1, so this is going to be growth as well. Okay, so exponential functions behave in specific ways, just the nature of the graphs. They're either always increasing or decreasing, and they're always concave up or concave down. And then they have pretty limited end behavior functions. So we're going to look at the general graphs here. And I've got 4 cases, 2 where a is positive, 2 where a is negative, 2 where the base is greater than 1, 2 where the base is less than 1. So this first one, I like to just do a little sketch, okay, is going to be exponential growth. Okay, so we know what that looks like, kind of like that. So this graph is always increasing. It is concave up. And then for the end behavior, we investigate the limit as x goes to negative infinity of our function and the limit as x goes to positive infinity. So as we go to negative infinity, our y values, our output values are approaching 0. As my x values increase without bound, we are going to infinity. For my exponential decay, the graph is going to look something like this. So this graph is decreasing and concave up. Then I can make those limit statements for the end behavior. So as we go to negative infinity, those y values increase without bound, so they're going to infinity. As x goes to infinity, then my graph is going to 0. The negative is going to affect the graph by reflecting this function over the x-axis. So the graph is an exponential growth, but then it gets flipped over. So from that graph, I can get all my characteristics. So from the graph, our graph is decreasing, concave down. As we go to negative infinity, the y value is approaching 0, and as we go to positive infinity, we're going to negative infinity. For this one, we're going to take the graph of exponential decay and flip that over. Okay, so just a reflection there, and then we can get our characteristic. So this one is always increasing, always concave down, and goes to negative infinity when x goes to negative infinity and approaches 0 as x increases without bound. Okay, next in section or topic 2.4, we manipulate our exponential functions using the properties of exponents. So what we're going to do is we're going to rewrite some formulas in the form y equals a b to the x. So the thing that we're looking at is the exponent just being a solo x. So we're going to use the properties of logs. So this can be rewritten as 3 to the x times 3 to the negative 2. Well, 3 to the negative 2 is the same as 1 over 3 to the 2, which is really 1/9. So I can write this as 1/9 times 3 to the x. So my a is 1/9, b is 3, and my exponent is there. Here I can rewrite this as 2 to the x times 2 cubed, which will be equivalent to 8 times 2 to the x. In my next two problems, I'm going to use the power to a power. So I'm going to rewrite this as 81 to the 1/2 to the x. And then 81 to the 1/2 is just the square root of 81, which is 9 to the x. Here, this is equivalent to 4 cubed to the x, and 4 cubed is 64. Right, and my next example is another way to manipulate exponential functions using the properties. So this is the number of people who have heard a rumor can be modeled by the equation R of m equals 321, 1.025 to the m, where m is in minutes. We're going to write an equivalent expression realized I had a typo. So we're going to write an equivalent expression where rather than measuring it in minutes, we're going to measure this in hours. So my initial amount is going to remain the same. Okay, but if we're doing this every minute and we're doing this for an hour, that means we're doing this 60 times, not times 60, but we're doing 1.02 times this, times this, times this, times this repeatedly. So it's going to be 1.025 to the 60 because in an hour we're going to be doing that a lot, 60 times. So I can rewrite that as 60h. Okay, here we're going to do the same thing, but I want it by the second. So if it takes a whole minute to do this, then we're only going to get a fraction of that. To the s, since we're measuring in seconds. So I'm going to rewrite this as 321 times 1.025 to the s over 60, or you could write it as 1/60th times x. In topic 2.6, we were introduced to the concept of a residual plot. So a residual plot gives the error in the actual data points in the regression equation. So here, an exponential regression was used to develop a model for two different sets of data. The two figures below show graphs of the residuals for each exponential regression. What does the residual plot tell you about the exponential regression for each set of data? And explain our reasoning. So, with a residual plot, if there is a clear pattern, like in this one, that means this is not a good fit. If there's a clear pattern, then there is a better equation out there. Okay, so this first set is not a good fit because there is a clear pattern, versus the second one, an exponential function, would be a good fit because there is no clear pattern. We just have a random values for the residuals or those errors. Section 2.7, topic 2.7, was about compositions of functions. So just taking functions or values and plugging them in to one value and then plug them in. So you always start on the inside. So h of f of negative 3, we evaluate f of negative 3. So I have three functions here. F is my graph, g is the table, h is this piecewise equation. So h of negative 3 is 2. Then I'm going to go to here. So 2, looking at my piecewise notation here, I'm going to plug into this equation. We get negative 3. Okay. Now g of f of 2. So again, I'm going to consult my graph. G of f of 2. So we've got a closed dot, open dot. So we evaluate at the closed dot, which is going to be 1. And then g of 1, according to my table, is 7. Okay, this notation just means g of h of 7. So h of 7, we're going to plug 7 into the root equation there. So that gives me the square root of 4, which is 2. And then I go to my table for 2, gives me negative 4. F of h of negative 2. So if I plug in negative 2 into h, I get 4 plus 1, which is 4. Okay, then we're going to go to the graph of f, and here we've got another interesting situation, but it's an open dot here and a closed dot here, so my function value there is 1. To my table, g of negative 4 is 5, and then g of 5 is 8. Okay, and then last we've got h of g of f of 0. So we're just going to go from the inside out. So h of g of h of 0, or f of 0, is 3. G of 3 is 19, and then we're going to take 19 and plug it into this equation. 19 minus 3 is 16, square root of 16 is 4. In topic 2.8, we talked about inverse functions. So one definition for our inverse is if f of a equals b, f inverse of b equals a. So we have a table of values where my inputs are here, my outputs are here for f. So the inverse, those are going to be switched. So f inverse of -1, we're going to look at the value of f that would give us a value of -1 and give the corresponding x. So that'd be 2. We're going to find 5 here, gives me a value of -3. Find 0, gives me a value of -1. Next, we're going to analytically find inverses. So just like with the numerical values, we're going to switch x and y. So when I do that, this will be x equals 4 minus 3y, and then we're going to solve for y. So my inverse, and there's different ways you could write that equation, but I'm just going to leave it as x minus 4 over -3. Okay, here, when I switch x and y, we end up with multiple y's, which is fine. So I'm going to multiply this over and distribute. So I'm going to have x, y minus x. Next, I'm going to move everything that has a y to one side of the equation, anything that doesn't have a y to the other side. So we're going to have xy minus 2y, and then I'll add that x over. Now I can factor a y out of all of these terms, and then I can divide. So my inverse equation is x plus 3 over x minus 2. So to get the square root, we're going to square both sides, subtract 1, divide by 2. So my inverse equation, using our notation, is that, or you could do 1/2 times x squared minus 1. The last one, we do have to have a restriction on the domain because this doesn't pass the horizontal line test. It's a parabola, so when I invert it, it's not going to give me a function. But if I restrict the domain, then we will have an inverse function. Subtract 4, divide by 3, and then we take the square root. So technically this would be plus or minus the square root, which is why that is not a function. We get out multiple values when we plug in single values. So because our restriction on the domain is when x is greater than 0, then here I want the positive portion of this. And you could consult the graph to confirm that. Next, we're going to graph an inverse function. So one characteristic of a function and its inverse graphically is that they're symmetric to the line y equals x. So that's good to know. Past that, just like with the table and the equations, I'm just going to switch the x and y coordinates. So here I have a point at -2, 6, which means on the inverse we're going to have a point at 6, -2. This point here at 2, 4 is going to go to 4, 2. This point at 5, -2 is going to go to -2, 5. And then my last point is at 7, -2, so we're going to be at -2, 7. So you see that whole thing gets flipped over that line, y equals x. Next, I've got some questions that would require a calculator. So a local radio station is running a prize drawing. A name is drawn from the entries each hour where the prize value increases each hour. The prize money each hour can be modeled by using an arithmetic sequence where the first prize occurs at hour 0. At hour 3, the prize is 200. At hour 8, the prize is 450. Drawing ends at hour 14. How much does the last award winner get? So I've got two known values. I'm just going to write it as A3 equals 200 and a 8 equals 450. Okay, so my general equation for an arithmetic is an equals ak plus dn minus k. Now you could find the common difference using like the slope formula, but I'm just going to plug it into here. Okay, so I'm going to say 450 equals 200 plus d, which I don't know, equals 8 minus 3. So my d is 50. Okay, then I can plug that in to get my general equation. And then plug in 14. So if we type all that in the calculator, since this is on the calculator section, we get a prize of $750. Okay. The world's cutest baby otter is discovered at a zoo in Colorado. The picture one zoo visitor took of the otter is going viral. The number of people who have seen the picture can be modeled by a geometric sequence. 4,500 people had seen the picture at hour 3, and 10,200 by hour 8. And we want to know how many people had seen it by hour 12. So my general equation for geometric is that. And then we'll plug in our values. Okay, so we're going to algebraically solve here. So I'm going to divide by 4,500, which would reduce to 102 divided by 45. So my r is going to be 102 over 45 to the 1/5. I'm going to leave it unsimplified when I put it in the equation to maintain calculator accuracy. So it's going to be the 1/5 times n minus 3. Then to find g of 12, we'll take 12, plug it in. Okay, and round to the nearest whole number here. So that gives me 19,630 if we round up there. Our next problem is going to be an exponential regression. So we have some data on some bacteria here, and we're going to use it to create a exponential regression. So for the TI-84, you're going to go to Stat and then over to Edit, and then you're going to enter your data. If you have stuff in there, you can do Clear Enter. So highlight your list 1, Clear Enter, and then enter in that data. Once your data is entered, we are going to run an exponential regression. So I'm going to get out of here. I'm going to go to that Stat menu again, but rather than editing, we're going to go over to the Calc menu and go down this list until you see exponential regression. Okay, we want list 1, list 2, because that's where we put our data, and then we absolutely want to store this regression equation. So I'm going to store it in Y1, which I can get to in the F4 shortcut key there, and calculate it. Okay, so I'm going to take that resulting equation. I'm just copying it down. Now this, I'm truncating it a little bit, but it's safely stored in my Y1. Get rid of anything else there. With all of those decimals. So when I do my calculations, I'm going to use Y1. I am not going to use this. Next, we want to predict how much after 10 hours. So we're going to evaluate Y1 at 10. Okay, so we get 8,664. Okay, next, researchers want to start a new experiment when the amount of bacteria is at 10,000. At what time does the exponential regression predict that will happen? So I'm setting my equation equal to 10,000. And again, we're going to be using our stored value, not the truncated version of this. To solve this equation, I'm going to graph it. There's different ways to do it, but I like graphing. So in my y2, I'm going to do 10,000. Okay. For my window, on my x-axis I have time. So I know at 10 we were at 8,000, so maybe I'll go to 15 for my time. For my y's, I need to be able to see 10,000. So I'm going to go to like 12,000 to give me a little buffer there. And then graph. Okay, so my solution is that intersection, which I can find using the calc menu, which is above trace. Find the intersection, and then just hit 3 quick enters because it says first, second, last, and I get 10.425 hours would be our units here. My last problem, the population of rabbits for a specific national forest was 21,000 in 2010. Since then, the population has increased by 3.2% each year. Write an equation for the population of rabbits, A, B to the T, where T is years since 10,000, and predict the number of rabbits in 2030. Okay, so my A is going to be the initial amount, so 21,209. My growth rate is 3.2, so in my exponential function, that's going to be 1.032 to the T. To predict for 2030, since this is since 2010, we'll plug in 20. Okay, and then let the calculator do this for us. And I will round to a whole number since we're talking about rabbits. But I get 39,821 rabbits. So that was your review covering topics 2.1 all the way through 2.8. Thank you for watching.